All right, so I want to do some demonstrations, and the first one I think I better do is Jasmin, which I don't believe I've demonstrated in this class. It's very simple. But I did update it a little bit to talk about what to do for this this machine we're using. So, all right, where's Jasmin? Here's assembly language. Fine. There it is. All right. So Jasmin is a simple Java-based simulator of an x86. And, you know, maybe I shouldn't even have this now that you're actually doing real assembly stuff in the assembly language CTF. But anyway, I had this, and I left it in this semester anyway. So on these machines here, Java is already installed, but Jasmin was not already installed. So that's why I put it here. If you're using our, actually, if I refresh this, hopefully I updated this. Yeah, if you're using the Windows 10 with tools, you don't need to install Java, but you do need to just install Jasmin. And so I downloaded Jasmin here. And it might already be in the tools directory too, but anyway, I just downloaded it again. And if you double click this, you get a simple 32-bit processor simulation where you can do simple code. And you make a new file. And so now you can put commands in here. So I'll just go down to here because I think we've been past that other stuff. All right, so here's a few commands. If you just copy it like Notepad is fine. And so you've got move EAX4, and you can run the whole thing here, or you can single step through it here. So if I do this, it puts 4 in EAX, and you can see the 4 over there. And by the way, I might be able to make the font bigger. Let me give it a shot. Configuration. Fonts. Let's see what choices I have. Oh, well, I got Arial Black. That looks pretty good. And let's try 16 and see what that looks like. Okay. All right. And now if I go back to here, maybe it only works if I make yet a new document. File, new. Yes, good. All right, now I can put in that stuff. All right. It didn't make everything big, but anyway, so if I move this, that puts, whoa, I ran the whole thing by accident. I'm going to reset it all. Now I'm going to do one step. So that puts 4 in EAX, which is there. Next thing is going to put 6 in EBX. Next thing is going to put EBX in the memory location pointed to by EAX, which is going to be 4. So when I do that, it's going to put it in memory over here. And looks like it did not run that command yet. This is the instruction pointer, the one that's highlighted. So I'm going to run that command there. And now it did put 6 here. Okay. So it took the 6 from EBX and put it in the memory location pointed to by EAX, which was 4. And you see it was a 32-bit word here. That's why these go up by 4s, like I was saying. They don't go up byte by byte because they assume you're going to refer to them as 32-bit words. And now I'm going to move EAX into ECX, so that should take this 4 and put it down there. And so it does. Now I'm going to add EBX into ECX, so it's going to add 6 into ECX, making it 10. And there you go. And then move ECX into EAX plus 4, which will take a 10 and put it in a memory location 4 plus 4, or 8 over here. So there you see it put a 10, which is an A in hexadecimal, over here. So, you know, that's the sort of thing. And you can use the stack, you can push things. So if I push EAX and push EBX and pop EDX, then this will push EAX on the stack. So I execute 1, and the stack in this simulator goes at the bottom of memory. So there you see there's a 4 down there. And now I push EBX, which is 6. So that puts a 6 on there. And now I pop EDX. That's going to take the top item on the stack, which is 6, and put it in EDX. And it does not erase it from the stack, but it moves the stack pointer so future things that are pushed on the stack will overwrite it. This is an example of the very common issue of data remnants. Many computer systems have leftover data from before, which is no longer being used, but is still present in memory, and can therefore be stolen from memory, leak when someone steals the hardware, and things like that. And that happens in RAM as well as on the hard drive. And it's always for the same reason. Just to make it faster, you don't bother erasing data when you're done with it. You just deallocate it and then let that memory be used again, because the people who design the systems are thinking about making them efficient for normal use, and they're not thinking about data remnants and disposal of them later. All right. So that's push and pop. And so there's a couple challenges here. I think I'll do this one, and maybe that'll be as far as I go on this demonstration. But this is good to get a little bit of practice with assembly code, so I can delete that and put in this. All right, so now I'm going to fill the registers. Let me go back, reset everything to the start. And so first I'm going to put 1, 2, 3, and 4 in the registers. 1, 2, 3, and 4. Okay, there they are, 1, 2, 3, 4. And then I'm going to push EABC, EAX, EBX, ECX, EDX, and then pop EAX, EBX, ECX, EDX. And the point is, of course, they're going to be in reverse order. When you push them, 1, 2, 3, 4, there they go, 1, 2, 3, 4. But when you pop them, they pop in reverse order. So it's going to be pop EAX, B, C, D, and you see they come in reverse order, 4, 3, 2, 1. The stack is a first in, last out system. If you wanted to use another pop, you could pop anywhere. You could also pop into ESI and EDI. I think it would be kind of crazy, but if I wanted to do more popping, what I would do is I would move some of this. So if I wanted to keep going, I would move it somewhere else, like move into, say, find an address available up here, like we were using this stuff as storage. So I guess I'd move into, say, 0 EAX, and then pop EAX. That's what you do. You don't have very many registers, especially in 32-bit code. So you can't really store anything for long in the registers. So what you do is you put things in registers, manipulate them, and then you put the results in memory. That's what memory is for. Popping into EDX is fine. Popping into ESP and EBP would be crazy, because that's what tells you what part of the stack you're using. So if you start corrupting those registers, you're going to lose control of your stack frame and start reading memory that's not allocated for your subroutine. So that would be in the realm of like self-modifying code that would be nuts. Good. Yeah, these are very good questions. All right. So, all right, and so there's some challenges. Here you take, you run this code, and it's actually going to put data on the console. So let me just download this code. I think it just appears here. Yeah, we can just copy and paste it. All right, so let's put that in here. Whoa, not there. Here, stop, Control A, Control V. There's the code. And the thing about this, there is something called a console down here, which is kind of cool. So you can actually see sort of text. You can print characters in there one and one. So EBX had a certain use. Yes, EBX, EBX did have a special purpose back in the days of Windows XP, which caused it to leak information. I think after certain calls, EBX contained a pointer to one of the configuration data structures that told you what area of memory you're in, so it would undo ASLR, something like that. Anyway, so here I'm going to reset. All right, so what happens here is I'm going to push a bunch of things onto the stack. All right, and I think the point is that this is something in the realm of encrypted or obfuscated data. So here's a bunch of data on the stack, and now it's going to move those to locations. And I think it's just memory 0 and stuff here. Let's see. Poppy AX. Yeah, it's XORing them. It's decrypting it and then moving it to some location. So I think the point of this is it's going to actually make a message spell out a message there as you run it. I was quite pleased to discover this. Yep, there it is. It's starting to print a message. There's an M, and more letters are going to appear when you play with this one. So there is a certain memory region that prints here, and I think it's just at the very start of 0. I think whatever you put right at the start of memory appears in that console thing. Yep, there's a 4D, and that's the M. So you can just put data here, and it'll appear in the console, so you can have printable messages there. And these challenges use that. So basically, it has a sort of encrypted message you decrypt, and there. So anyway, there's a couple of flags to find by playing with the assembly code in Jasmin, and it gives you a little bit of practice. So that's it for Jasmin.